Le Chatelier's principle states that if a system at an equilibrium is subjected to an external stress, the equilibrium will shift to minimize the stress. There are three different changes that can cause a stress in an equilibrium. A change in the concentration of either a reactant or a product, the change in the pressure or volume as it relates to gases, or a change in temperature. Notice that these types of stresses look very similar to those discussed in terms of factors that affect reaction rate. Please take careful notice throughout this lesson as to the differences between the two questions so that you're able to identify what type of question you'll receive in a test situation. As we discussed in the last lesson, in a system at equilibrium, the concentrations of the reactants and products do not have to be equal. In fact, most times they're not. The concentrations of reactants are either greater than or less than the products. The only thing that is equal in an equilibrium is the opposing rates of reaction. Recall that the definition of a dynamic or chemical equilibrium stated that the rate of the forward reaction and the rate of the reverse reaction must be equal. The position of an equilibrium depends on the relative concentrations of the reactants and the products, and you could be asked to make a statement about the position of an equilibrium in an assessment. If the concentration of the reactants is greater than the concentration of the products, then we would say that the position of the equilibrium lies to the left. If the concentration of the products is greater than the concentration of the reactants, then we would say that the position of the equilibrium lies to the right. So given a concentration of a reactant and a concentration of a product, you can use these two concentrations to make a statement about the position of the equilibrium. Le Chatelier's principle states that if a system at equilibrium is subjected to a stress, the equilibrium will shift in a direction to relieve the stress. Or if a system is subjected to a stress, the equilibrium will shift in a direction to do the opposite of the stress. And recall that there are three different types of stresses: a change in concentration, a change in pressure/volume, or a change in temperature. We are going to look at each one of the stresses individually by starting with changes in concentration of a reactant or product. From the collision theory in the kinetics chapter, if you increase the concentration of a reactant, then there is an increased number of collisions due to an increase in the number of particles. Thus, the forward reaction rate is increased and the equilibrium will shift to the right. The stress on the system is excess reactant, and the system responds by trying to remove that reactant. In order to remove that reactant, the reaction shifts forward, producing more products, thus attaining a new balance. Let us look at the equilibrium that's established when hydrogen and iodine react to create hydrogen iodide. For this example, let's say that the stress caused on the system was an increase in the concentration of hydrogen. According to Le Chatelier's principle, when a stress is given on a system, the system will shift to oppose the stress. If the concentration of hydrogen has been increased, according to Le Chatelier's principle, it will shift in order to decrease the concentration of hydrogen. In order to decrease the concentration, the system must shift to use it up. In order to use up the hydrogen, the system therefore must shift to the right or towards the products in order to cause the concentration of the hydrogen to go back down. When the equilibrium shifts to the right, it's shifting towards hydrogen iodide. As such, the concentration of the hydrogen iodide will now increase. When it shifts to the right, it's also shifting away from the iodine. If it's shifting away from the iodine, the concentration of the iodine will decrease. What happens when the stress that's introduced to the system is an increase in the concentration of hydrogen iodide? If the stress on the system is an increase in the concentration of hydrogen iodide, according to Le Chatelier's principle, the system will want to do the opposite. So the system will want to shift so as to decrease the concentration of hydrogen iodide. In order to decrease the concentration of hydrogen iodide, the equilibrium must shift to use it up. In order to use up hydrogen iodide, the system must shift to the left. When the system shifts to the left, the concentration of the hydrogen and the iodine will both increase since we're shifting towards those. What about the situation when the stress on the system is a decrease in the concentration? In this case, we're going to look at a decrease in the concentration of hydrogen iodide. If we decrease the concentration of hydrogen iodide, according to Le Chatelier's principle, the equilibrium will want to do the opposite, or increase the concentration of hydrogen iodide. In order to increase the concentration of hydrogen iodide, we have to make more hydrogen iodide. In order to make more hydrogen iodide, the equilibrium must shift towards it, or to the right, or towards the products. Since the equilibrium is shifting towards the products or away from hydrogen and iodine, the concentrations of both of these will therefore decrease. Shifting in an equilibrium as it relates to Le Chatelier's principle can also be shown in graphical form. Let's say, for instance, that the stress caused on a system is an increase in the concentration of hydrogen iodide. This stress was caused in a lab situation. Therefore, on the graph, it's shown by this very steep increase. According to Le Chatelier's principle, if you increase the concentration of hydrogen, the equilibrium will want to do the opposite and decrease the concentration of the hydrogen. In order to decrease the concentration of the hydrogen, the equilibrium must shift to use it up. In this case, that would be towards the right. Since we're shifting towards the ammonia, the concentration of the ammonia will increase. And since we're shifting away from nitrogen, the concentration of the nitrogen will decrease. This can also be shown in the graph. Notice that we said that the concentration of ammonia will increase. And as you can see, the ammonia slightly increases in the graph. It's not a straight up vertical line like hydrogen because hydrogen was the stress. It was added. The shifting causes a more gradual change. We also said that the nitrogen will decrease since we're shifting away from it, and the hydrogen will decrease as well. And those are also shown by gradual changes in the graph. Once the shifting, according to Le Chatelier's principle, has taken place, remember that Le Chatelier's principle states that the equilibrium shifts to attain a new equilibrium, and this is then shown later on by horizontal lines. To consider the effect of temperature on equilibrium, we have to consider whether the reaction is endothermic or exothermic. Recall from the kinetics chapter that an endothermic reaction is the addition of heat, and an exothermic reaction involves the removal of heat. Let's look at the equilibrium that's established when nitrogen and hydrogen reacts to cause ammonia. Notice that in this reaction, heat is released, 92 kilojoules of energy is released, and this is considered an exothermic reaction. Let's say, for instance, that the stress caused on the system was an increase in the temperature. This means that we are increasing the 92 kilojoules. According to Le Chatelier's principle, the system is going to want to shift to do the opposite, which means the equilibrium will shift to decrease the 92 kilojoules. In order to cause the energy to decrease, we have to use it up. And in order to use it up, we have to shift away, to the left, or towards the reactants. Since we're shifting towards the reactants, the concentrations of the nitrogen and hydrogen will decrease, and the concentration of the ammonia will decrease. Therefore, you can consider a temperature term in a balanced chemical equation the exact same way we considered concentration. The last stress that can be caused on an equilibrium would be a change in volume or pressure. Recall from the kinetics chapter that if you increase the volume, that's the same thing as decreasing pressure and vice versa. Also recall that a change in pressure only affects equilibrium systems that includes gases, since solids and liquids are incompressible. According to Le Chatelier's principle, when the pressure on an equilibrium system is increased, the reaction is driven in the direction that will relieve the pressure. Therefore, an increase in pressure, for example, will shift to the side with the least moles of gas. Why? Because if you increase the pressure of the system, according to Le Chatelier's principle, the equilibrium will shift to cause a decrease in pressure, and less pressure will be present on the side with less moles of gas. Therefore, If you increase the pressure, the system will shift to the side with the fewer moles of gas. If you decrease the pressure, or if the stress is a decrease in pressure, the equilibrium will shift to the side with most moles of gas. And if the moles of gas are equal, an increase or decrease in pressure will not alter the position of the equilibrium. Let's look at the example of sulfur dioxide reacting with oxygen to create sulfur trioxide. What happens in this case when we increase the pressure? Well, if we increase the pressure, the first thing we need to do is count up the number of moles of gas on either side of the equilibrium arrow. In the example that we're looking at, we have 2 moles of sulfur dioxide and 1 mole of oxygen to give us 3 moles of gas in total on the reactant side. On the product side, we create 2 moles of sulfur trioxide, or 2 moles of gas in total. If we increase the pressure on the equilibrium will want to shift in order to decrease the pressure. In order to have less pressure, we have to shift to the side with less moles. Therefore, it's going to shift to the right or towards the products. When it shifts towards the right or towards the products, it's shifting towards sulfur trioxide, and therefore the equilibrium concentration of sulfur trioxide will increase. It's shifting away from sulfur dioxide and oxygen, therefore these concentrations will decrease. The last 2 changes that we're going to consider is adding a catalyst or changing the surface area. Recall from the beginning of this video, I only talked about 3 possible stresses: a change in concentration, a change in pressure or volume, and a change in temperature. Therefore, whenever we talk about catalysts or changes in surface area, I like to consider these trick questions. And the reason why these are considered trick questions is because both a catalyst and surface area have no effect on equilibrium. So a catalyst is something that we add to a reaction in order to speed it up. We talked about that in the kinetics unit. Therefore, a catalyst added to a reaction has no effect on equilibrium. The reason it has no effect on an equilibrium is because when a catalyst is added to a reaction to speed it speeds it up by lowering the activation energy, as you can see in the diagram. However, it lowers the activation energy by the same proportion in the forward direction as it does in the reverse direction. Therefore, it speeds up the rate of the forward and reverse processes equally. Therefore, a catalyst has no effect on the position of the equilibrium. And if you're given a question with an equilibrium and asked to predict the changes when a catalyst is added, you would have to answer that it will have no effect on the position of the equilibrium because it speeds up the rate of the forward and the reverse processes equally. A change in surface area has the same effect. Changing the surface area of a reactant or product has no effect on the equilibrium. The reason changing the surface area of a reactant or product has no effect on equilibrium is because if you recall back to a change in concentration, pressure, or temperature, we've always been increasing or decreasing concentration, pressure, or temperature. If you change the surface area of a reactant and product, you're not actually adding any more or less of the reactant or product. You're just simply exposing more particles. However, the total number of particles remains constant and therefore it will have no effect. At this point, I hope you understand why an equilibrium shifts in a certain direction based on the stress and why the changes in concentrations occur afterwards. The last thing that we need to straighten out for Le Chatelier's principle is how to answer a question in an assessment situation. To do this, we're going to go through several examples. The first one is to predict the changes that happens when the temperature of the reaction mixture is increased in an equilibrium between PCl5, PCl3, and Cl2. Whenever you answer a question about Le Chatelier's principle, you must always start the answer with according to LCP, or according to Le Chatelier's principle. Then you must make reference to the stress in the system as well as why the equilibrium is shifting. For instance, in our question, when the temperature of the reaction mixture is increased, we're going to start with according to Le Chatelier's principle. If you increase the temperature, so we're making reference to the stress that started the question, the equilibrium or the system will shift to decrease the temperature. More or less, we're reiterating the definition of Le Chatelier's principle. The definition of Le Chatelier's principle states that if a stress is placed on a system, the system will shift to oppose the stress. In our question, the stress was an increase in temperature, and to oppose it, we would have to decrease the temperature. Next, we have to make reference to the direction that the equilibrium is going to shift in. So we may have to do some workings for that. In this question, we were told that the temperature is increased. That is the stress. According to Le Chatelier's principle, the equilibrium will shift to do the opposite. That would be to decrease the temperature. In order to decrease or use up the energy, we must shift away from it, and shifting away from it would be towards the right. Therefore, in our answer, we have to say, in order to decrease the temperature, the system will shift away from the heat to the right, or you can say towards the products. The last thing we need to make reference to in our answer is the changes in the other equilibrium because of the shift. Since we're shifting towards PCl3 and Cl2, their concentrations will increase. Since we're shifting away from PCl5, its concentration will decrease. So in our answer, we're going to say, as such, the concentration of PCl3 and Cl2 will increase, and the concentration of PCl5 will decrease. And recall that a square bracket means concentration. Let's go through the next example. PCl3 is removed from the system, so the stress is the concentration of PCl3 is decreased. If the concentration of PCl3 is decreased, the system will shift to increase PCl3. And in order to increase PCl3, we have to make more of it. So again, we're shifting towards the right. When we shift towards the right, we're making more Cl2. We're shifting away from PCl5, so that concentration will decrease. So we can put this all together now in a proper answer. Since it's all about Le Chatelier's principle, we're going to say according to LCP. We also need to make reference to the stress that caused the question, as well as the oppose the stress. So we're going to continue with, if PCl3 is removed from the system will shift to increase PCl3. The next sentence we have to say which direction it's shifting in and why. To increase PCl3, the system will shift towards the right. The last sentence must make reference to the changes in the other concentrations. So as such, PCl5 will decrease and Cl2 will increase. The next example, iron nitrate is added to the system. This is a more difficult question, which was pulled from a prior public. And in order to complete this question, you must use your solubility chart that's on the data table provided in your data booklet. And I strongly encourage that you take that out now so that you can understand how we answer this question. In this example, iron nitrate FeNO3 is added to the system. And the first thing we need to look for is if either of these ions, Fe or NO3, is in our equilibrium. And notice that it is not. So in this example, we're not actually adding anything that's existing in the equilibrium. This is where the solubility chart comes in. If we're not adding something that's participating in the equilibrium, there is a possibility that we would be adding something that would react with something in the equilibrium. So right now, you need to use your solubility chart to see if any of the ions in the equilibrium will react with any of the ions that are in iron nitrate. Recall from Chemistry 2202 that iron nitrate is an ionic compound that will dissociate in solution. Therefore, iron nitrate actually exists as Fe3 positive and 3 NO3 negative. Therefore, you have to see if either one of these will react with any of the ions that are present in our equilibrium. By looking at your solubility chart, you should notice that Fe3 positive, when it reacts with hydroxide, forms a precipitate or a solid compound, which means that the iron added from the iron nitrate will actually cause a reaction with the hydroxide. So we start off our answer with, when iron nitrate is added to the equilibrium, the iron ions will combine with the hydroxide ions to form a precipitate of iron hydroxide, solid. Therefore, this reduces the amount of hydroxide aqueous that's available to the equilibrium. So more or less, this is a very long-winded way for us to say the concentration of hydroxide has been decreased. Since the concentration of hydroxide has been decreased, the equilibrium will want to shift to increase the concentration of the hydroxide. And in order to do that, it must shift to the right, or towards the products. When it shifts towards the products, the concentration of Cr2O7 will increase, and the concentration of H positive and CrO4 will decrease. Therefore, we continue with the same answer as above. According to Le Chatelier's principle, if the concentration of hydroxide is decreased, the system will shift to increase the hydroxide. So we talk about the stress and the opposite of the stress. Then we have to talk about the shifting direction. So to increase the concentration of hydroxide, the system will shift towards it to the right. As such, Cr2O7 will increase, and H positive and CrO4 will decrease. The last example we'll look at will involve that of pressure. The pressure of the following system is increased. Recall for pressure that it only works for gases, so you do have to go through your equilibrium and identify only the gases. And it's only the moles of gases that you're going to count. If we look at the reactant side, the coefficient of PCl5 is 1, so we have 1 mole of gas on the reactant side. We look at the product side, and in total, we have 2 moles of gas. If the pressure is increased, then the system's going to want to shift to decrease the pressure. And in order to decrease the pressure, it's going to shift to the side with less moles, or towards the left. Since it's shifting towards PCl5, PCl5 will increase, PCl3 and Cl2 will therefore decrease. So to give a full mark answer, we of course start with, according to Le Chatelier's principle, if the pressure is increased, then the system will shift to decrease the pressure. In order to decrease the pressure, the system will shift to the side with the least number of moles, which is the left. As such, PCl5 increases, and PCl3 and Cl2 will decrease. This is more or less a great recipe to remember in order to get full marks on an assessment as it relates to Le Chatelier's principle. And I strongly encourage that you practice this, as this topic can be quite difficult, in the following worksheet.